Okay, so yesterday we looked at two types, another two classification algorithm, which were the KNN, that's the K nearest neighbor, and the support vector machine. And I remember one of the things we said on the KNN is that KNN helps to, most times KNN stores the training data. It doesn't really build a model. It stores the training data, and when we want to make prediction, when we supply with a new observations or new data point, it will take those new observations and look for the nearest data point, the data point in the training set that is closest to it, and then it will assign the class to it. And if we are looking at more neighbors, more than one, like 3 or 5, it's going to look for 3 or 5 neighbors closest to the new data point, and then voting will come in. Majority of the majority class will be assigned to the new data point. And also we look at the support vector machine, where we said the goal was to maximize the margin. And when we say the margin, that's the distance between the decision boundary and the support vectors. And support vectors are the observations closest to the decision boundary. So we said the main SVM or support vector machine has 2 variants. We have the linear SVC, which functions similarly to the linear models. And we have the support vector classification or support vector classifier that make use of the kernel trick, which is a way of computing polynomial degrees without actually adding them to the data. So today we want to consider another type of classification algorithm, which are very, very popular and very powerful. One that is called decision tree and the ensemble methods. So what is a decision tree? Why are we using decision tree? And what is the disadvantage or the drawback associated with decision tree? Decision tree, just like logistic regression, KNN, or support vector class machine, is also a classification model, although it can be used for regression also. So, but I'm going to focus on the classification aspect of it. So it works by learning a series of if-else questions. We call those if-else questions tests. I don't mean test data, TEST, just test. We call them if-else. Why do we call them if-else? Now look at this diagram. That suppose the goal is to, let's say we want to classify animals to be any of these 4 animals, whether it's a bear, ox, penguins, and dolphins. Suppose that's our goal.
Your email is showing on the screen. Your email. That's what it's showing.
My email.
Yes, it's showing a browser screen with your Gmail. It's not showing the what you're teaching. Like, I don't know.
All right, so what I'm saying is for logistic regression, it works by, for decision tree, it works by learning a series of if-else questions and leading to a question. What do we mean by that? That is like a normal day-to-day stuff, like, okay, you want to build a model to classify animals to belong to any of these 4 animals. What are the 4 animals? Bears, ox, penguins, and dolphins. So we want to build a model that will be able to classify any animal to be any of these 4. So we start by asking questions. Okay, like the first question we'll consider is, okay, that does this animal, does it have a feather? You know, if the animals have a feather, then true comes to the left, right, false comes to the right, things like that. So that would divide the animals into, so we now begin to look. Out of these 4 animals, which one have feathers? Bears doesn't have. Ox, yes. Penguins, yes. So those ones can be categorized. Those ones can move to this left. and the force, the bears and the dolphins can come to the right. Then we'll ask another question again. Okay? The two animals, we know the ones on the left are the ones that have feathers. Can they fly? True, that becomes hawk. False, out of the penguins and hawk, false, penguin cannot fly. Out of the bears and the dolphins that are on the right, which one has fins? Then we know dolphin has fins. That's true, false. Bear doesn't have. Things like that. So what are these graphs that I'm showing you here? The first node you are seeing, these are nodes, okay? These are nodes in a graph. And the line to each, the line here are the edges, okay? So this first node is what we call the root node. The root node, that's the first node in the graph, okay? And when we say root node, there's nothing going on in the root node. All you have are the number of observations in the data, how many classes are in the data. That's where the question starts from. All the other node, apart from the root node, remember the root node is the first node. All the other node are called leaf. Leaf. They are leaf node. But there's something we call pure leaf. What do we mean by pure leaf? Pure leaf are when the observations, the data points in that node all belong to a single class. I will show you an example. They all belong to a single class. Like suppose you want to build a model to predict whether a patient survived or not, the Titanic problem, the Titanic issue that happened. If all of the data points that falls in this, let's say the second node here, which is on the left, if all of them belong to just one class, like survived, then we say that node is pure. Normally, a pure node should be where the decision will stop. Normally, that's where the decision will stop. That's normal. But a decision tree will try as much as possible to keep going until it gets to a pure node. But sometimes it can overfit. So the main problem, I will show you how to implement this. I will show you so you will get a better understanding of it. It may still be unclear. But the decision tree has a major problem. The problem of decision tree is that it normally overfits. It normally overfits to the training data, meaning you will have very accurate results on the training, but maybe not so good on the test data. So that's the issue with decision tree. But let's look at how to implement it. So that's the major thing. But how do you solve it? I'll show you like two major ways. One is to reduce, one is to apply what we call pre-pruning, meaning because if you allow the decision tree will continue building and building and building and building until all leaves are pure. And most times when all the leaves are pure, remember how the leaves are pure means all the observations in that node belong to a single class. But most times when all the leaves are pure, it leads to overfitting. So one of the solutions is to stop the tree from being fully built. Like we reduce the depth of the tree. While it's building, we just cut it off. We reduce it from being, we stop it from being fully built. But another solution is what we call a ensemble method, which we are going to look at, which is a collection of trees. Instead of building a single tree, we want to build multiple trees and then aggregate the result. That's where ensemble comes in. But what is the advantage of decision tree? Decision tree is very easy to interpret and you can also visualize it. We can visualize it, okay? Unlike other machine learning models. So let's see how to implement it. I'm going to use the iris data to implement the decision tree. So from scikit-learn data sets, import the iris data, okay? Then we also import tree if you want to visualize the tree. So that's what this second line is helping us to do. From scikit-learn, import tree. This is the data set, the iris data. Then this is the decision tree classifier. So from scikit-learn tree, we import decision tree classifier. The decision tree classifier is the name of the algorithm that will help us with, that will build the decision tree model. Okay, so this is the data. I'm using the return XY to be true to partition the data into X and Y. If I set this to be false, then it will come like normal data that we normally do. Like if I do iris, then we'll not be able to, then the data will not be partitioned into X and Y. I just want to show you. So we can do iris keys. If you do that, then you're going to have you can see, you're going to have the normal one where the data is stored in data, the target is here, target names is here, feature names is here. You can go ahead like we normally do. But if we want it to be partitioned into X and Y, there is an argument inside this load iris data. See, return XY by default is false. If we set it to be true, we're going to have the data partition into X and Y like that, where the X will be the variables, the Y will be our target. So I just want to show you. So let's do that. So the data now have X and Y, and then we can as well. So I just want to show you I want to visualize the tree so that you see how to build or visualize the tree. So here I create an instance of the decision tree classifier. I set the seed, random seed equals to 0, you can use any other number. So let's fit it, clf.fit, then we pass in our X and Y. I'm not splitting it into X train, Y train, because I'm not really interested in building the tree yet. I just want to build the tree and visualize it for you. If you want to build a model, really, obviously, you will divide the data into X train, X test, Y train, Y test. But I just want to quickly show you to visualize the tree. So let's run fit on it, and then let's visualize the tree. Remember to visualize, we use matplotlib.pyplot as PLT. Here I'm creating a figure. So to plot the tree, we'll call this tree. So we'll call the tree dot, press tab. You will see the plot tree method. So then you can pass in your decision tree classifier, which is this CLF, the instance of the decision tree. So then we can do plt.show. So, and then you can see the decision tree. So, are you with me, Nathaniel?
Yes, sir.
Okay. Now, this first node, like I was explaining earlier, is the root node. Now, look at what we have there. So here is telling us we have 150 observations in the data, 150 data points. And fortunately, 50 of them, like they are equally classified. Like we have 3 classes. We have the Virginica, the Setosa, and the versicolor. And each of those classes have 50 observations. This is not always the case, but for this particular data, each of the classes have 50 observations. That's what this is telling us. Now look at the first question that is shown here. X represents the features, okay? The data. Now, X of 3 means the third observation. This is asking us that, is the third observation less or equal to 0.8? Like, is the third feature, the third feature, is the value of the third feature less, because we have 4 features here. We have the sepal length, sepal width, petal length, and petal width. It's asking us if the third one is less or equal to 0.8. Based on that, true comes to the left, false comes to the right. The true Guinea, that's 0.0 samples. So for those true, we only have 50 observations that is true. And but for those 50, unfortunately, all the 50 belong to a single class. And when we have all the observation belonging to a single class, that was what I was referring to, pure leaf. Pure leaf. You can see the remaining ones are 0, 0. The 50 belongs to a single class. So at this second node, this is a pure leaf. Normally, that's where the tree is supposed to stop when it gets to pure leaf. So, but because that's not the end, this is not the end. The tree quickly moved to the one at the right to continue, since that one is an impure node. You can say 50-50. So it quickly move and then move to the right and then continue. See, the arrow is from the right now. It's supposed to be from the left. But because this node at the left is a pure leaf, it switched to the right because it hasn't yet, it's not fully built. So that's what will happen. When you allow the tree to be fully built, when it gets to pure node and it has not really gotten to the final answer, it will switch to impure node and continue building until it gets to this final node where all the leaves are pure. You can see this first node is pure. The two samples only belong to a single class. This one is also pure. The one sample only belongs to another class, which is only belongs to a single class. So when you allow the tree to be fully built, even if it come across a pure leaf, it will switch to the other one and continue building until the tree is fully built. So thereby giving us a very good accuracy, but most times that will lead to overfitting. Yes. So, but what I said, how do you resolve that? You resolve that using a method called pre-pruning, meaning you don't allow the tree to be fully built. We can control that using an argument called the max depth. Let me show you with another data here. Let's show you. Let's implement it, and then you will see what I'm trying to talk about. Let's use another data called the cancer data from scikit-learn data sets. Okay, so here we instantiate the data, we load the data. So because I want to build my model, I'm splitting my data into training and testing. You are familiar with this one already. From scikit-learn model selection, import train test split, and then we use the train test split to split it into X train, X test, Y train, Y test. So we are splitting the cancer data into X train and X test, and the cancer target into Y train and Y test. I explained this stratify equals to the target yesterday. I don't know if you still remember, but if I can remind you, this is to enables the proportion of the target in the original data to be maintained in the data you are splitting. In case, although it may not really make much sense for this one because this data, the targets are equally spaced, like 50, 50, 50. But in most data you will come across in the real world, this data will not be equally spaced. Like they won't be equal in the data. One class can be more than the other. So it's always a good idea when one class is occurring more than the other, just specify stratify to be your target variable in the data. Okay, then we set the seed for reproducibility. Are you with me? Okay.
Yes, sir.
All right, so let's go ahead and build the tree. So from scikit-learn tree, import decision tree classifier. So, and then I'm creating an instance of decision tree classifier. I call it DEC underscore tree. Then let's build it by calling fit on the X train, just like we normally do for the other ones. So it's just the same format. And then we can check the accuracy on both the training and the testing. So here, I want to check the accuracy on the X train and on the X test. So let's run this. So look at the results. We're having 100% on the training, 92.3% on the test. What do you observe in the results? Does it generalize
Okay,
well?
it
Does it pass?
overfits a
Okay.
little.
Yeah, it overfits because it's showing us that the model is accurate 100% on the training set, but on the testing is 92.3. That's a clear indication of overfitting. So that's what happens when you allow the decision tree, you allow the tree to be fully built. Yes, we can visualize it, but it will be, I mean, we can show it if you want to show it. We can show you. We can call on the tree plot tree and then pass in this tree that we just built, and then we can do the plt dot show. See, so if I create a figure, maybe to make it so that we see it, fig plt dot figure, and then we can specify the fig size. Maybe we'll do 15 by 10. Okay, look at it now. So this is these variables, this data has about 30 features. So if you do counter.data.shape, you'll see it has 30 variables. So you will see along some of the questions, is asking if the 27th variable value is less or equal to 0.142, like that. So if you allow it to be fully built, the decision tree will overfit. It will make sure that all the last node are pure leaves. And if you check the last node there, you will see that they are all pure leaves. This one sample belongs to, all the one belongs to a single class like that. So what can we do? There is an argument here in the decision tree. Let me show you the documentation called the max depth. That max depth, if you do not set it, the tree will be fully built and it can lead to overfitting to the training data. But if we want to pre-prune it, like I said, that we don't want the tree to be fully built, we can set the depth of the tree. From this, we saw that the tree is using 1, 2, 3, 4, 5. It's using 5 depth. You don't count the root node. 1, 2, 3, 4, 5. It's using 5 depth to build it. What if we reduce the depth to 3 or 4? Let's see the effect on the accuracy. So I'm going to copy all of these, and I will just rebuild, just set the tree, set the maximum depth to, let me use 3 for you to see max depth. Yeah, let me use 3 and then see. Now, what do you observe about this result? What do you observe compared to the previous one?
Okay, the training has dropped, the training accuracy and the test accuracy has increased.
Yes, so that's the effect of pre-pruning. So what you are trying to do, you are trying to reduce the depth of the tree. We could also try 4. So we could run a for loop on max depth to see the effect of the accuracy, just like we did for logistic regression when we're trying to check the values of alpha, or even for last one, we're trying to check the effect of C, of alpha, logistic regression to check the effect of C. We will run a for loop. We can set maximum depth, like that. I don't know if you remember what I'm talking about. So
Yes, I do.
yeah, so you could also do that for this max depth just to see. So we can also set the seed so that we can be having, so maybe we set for 4. He's reducing now. I know for 5 will be almost the same thing as before. let's see. So you can always try, just try, uh, just try, you know, you run a for loop like that. But so that's just the idea that, okay, you have to, you know, let me change the seed and rerun this and see if I will have a better one. Okay, see the same thing. Okay, so that's it. So you can always, you know, you can always, what?
Okay, I tried changing my max depth, although my training accuracy remained as 1, but the test accuracy was increasing.
It's possible. Uh, it's possible. So, but the main thing is when you change that max there, if you reduce it, it normally most time reduces overfitting. That's what we call pre-pruning. We are trying to cut the tree from being fully built. That's exactly what we are doing. Are cutting the tree from being fully built. That's what you are doing when you set the max depth. So you can run a for loop through it so that and use max depth of 2, 3, 4, and 5, you know, like that. And then for each one, run a for loop to build the decision tree. Store the train accuracy and the test, and you can visualize it like that. And you can just show the tree like I already did here, you know. So we can also check, there's an attribute we can also check, which we call the feature importances. That is, you want to check which of the variables, we have 30 variables, but which of these variables does decision tree selected to be very important to achieve the goal of predicting which patient, whether the patient has cancer that is malignant or benign. So there's something what we call the feature importance. How do you do that? Call the decision tree instance. If you press tab, you see feature importances. If you run it, this gives you values from 0 to 1 that is equal to the length of the variables you have in the data. Now, the higher the value, the more important the variable is. So, but let's visualize it so you can understand it better. But that's how to get feature importance. All these value represent value for a variable. If it's 0, that means the decision tree is saying this variable is not that important. It doesn't mean the variable is not important, but decision tree is not seeing it as being important to use to build a tree. So we'll still revisit this when we look at example of decision tree. Okay, so let's plot it so that you can see it very clearly. So all I'm just doing, you can see I'm still doing the decision tree importances. I'm only plotting it, and I want to use dot because by default, remember the plot method will give you a line plot. So you're using a circle dot. All this one, I'm just trying to plot to include the names of the variables in my plot. That's all I'm trying to do. So let's run it. You can see by decision tree is only considering a single variable as the most important. That's the worst perimeter. It's called the worst perimeter. It gave you like 0.75. Another one, maybe like worst concave point. That one, but that one is around maybe 0.1 something. So most of the variables, they have values close to 0. That means decision tree is not really using those variables as being very, very important. It's mainly considering this worst perimeter as the most important. So that might be why decision tree is not so much giving us a good result. A good result. That may be one of the reasons. So, but let's look at what we call the concept of examples of decision trees, and the one we focus on is random forest. Random forest is part of a method we call bagging. And I will explain what I mean by random forest in the concept of bagging. And what I mean by bagging. Okay, so when we say random forest, one, it's also making use of decision tree. Instead of a single tree, can we have forest of trees? That's all it's looking at. Can we have forest of trees where each tree in the forest will be a decision tree? We know a tree will overfit, but can we have many independent, many different trees to produce result, and then at the end we aggregate the result? That's how the random forest is doing. So each tree in the forest, in random forest, is a decision tree, but each tree is different. How is it different? That's where the name random comes in. Each tree is randomly selecting variables to build the tree. Those variables are selected with replacement, a method called bootstrapping. Bootstrapping means you are randomly selecting something, but you are replacing it back. So that way, some variables will be selected to build the tree. Some will not even be selected. Some will be selected multiple times because you are replacing it back. So the goal of random forest algorithm is to make sure that each tree in the forest is different. So each tree is just like we have 10 people who is good like you to build a model, but each of you have different talents, but you are building, you are working together to achieve the same goal, but each of you are doing something different, but targeting the same goal. So at the end, we'll gather all the output of the 10 of you and aggregate them. That's all it's doing, because there's no point gathering 10 people who have the same ability like you. Obviously, that will not make much sense. Do you understand? That's what random forest is doing. It's building 10 different decision trees. But so each tree is different. Each tree will overfit on the training data, but at the end, we will collect the result of all the trees and aggregate them together. If we're using the random forest for a regression problem, then at the end, we'll take the average of the tree, of the result. But for classification like we are doing here, what is going on under the hood, at the end of it, they are voting. They're actually voting. So like which one has the highest accuracy, things like that. So, but it's a form of soft voting. And the voting is based on probability measure. Like, well, what's the probability of which tree that will have the highest, make accurate prediction, things like that. But one thing I wanted to take out of decision random forest, one is a collection of decision trees. Each tree in the forest is different, and also that is using a bootstrapping method. That is a method that randomly selects the variables with replacement to build the tree. Okay, but the disadvantage is like you cannot visualize the tree for random forest, just like we did here. You cannot do that because by default, the number of trees in random forest is 100 by default. And the more the number of trees in random forest, the better the result. However, the more the trees, the slower it is to train. So imagine if we have 100 of these, it cannot occupy your screen. So this is a single one. We now have 100 of this. So that is it. So if you're interested, if your goal is to visualize the tree, then you should use decision tree. But if your goal is to get very good result, then you should use random forest. Okay, so let's implement it. So to do that, we do from scikit-learn example, we import our random forest classifier. For regression, you do random forest regressor. I also remember after this class, I'm going to put the project, at least the first project on in your Canvas dashboard so that you can walk through that during the week. You can use any of the different models we have been considering, like GC regression, all of that. So I'll put a project for you so that when you are able to do the project, at the end of it, you'll be able to get your certificate. All right, so you can use all of this code and some of these models we have been using. You are going to try all of the models before you come out with the best result. Okay? Okay,
Yes, sir.
so let's instantiate it. Let me use RF, random forest classifier. Let me use the default, and then let's train it. rf.fit, then we'll pass in the X train. I hope you are getting something out of this class. And Y train. So now it also overfits, but the accuracy on the test comes up, it like increases. Let's check this. So we should even set the seed also. But look at the max depth. So by default is none. You can see the number of estimators is what tells us the number of trees. By n estimators, it refers to the number of trees. By default, it's using 100. So let me check the seed. Let me set the seed for reproducibility. And then the max depth, maybe I should try 3. So this reduces, and also this reduces a bit. So we can try maybe 2. Oh, the test is also reducing 2. But to me, this is not overfitting as much. 96.5 to 93. Let's check 4. 99.5 to 94.4. So that's still overfit. So the result should be between 2 and 3. Result should be between 2 and 3. So this is better. 98.8 and 94.4. But you cannot, there are a couple of things that you can adjust. We can adjust the minimum sample split, the maximum features, the mean number of nodes. There are a couple of things that we can adjust there. Okay, so to get a good result. But that's how, so that's what random forest. So random forest normally perform better than decision tree anyway. It performs better. So that's it. So this is how to implement it. You can play, don't worry, I will still look at a topic called model hyperparameter tuning that will mainly discuss how to tune the hyperparameters of your model to get a better accuracy. We can also visualize the feature importances like we did for decision tree. But you see that random forest will be better. Let's try this. So look at it. Compared to this diagram, where only the worst perimeter is considered as very important, random forest consider quite a number of variables as very important. Even though the worst perimeter is still the most important, just like decision tree. But look at other ones, like the worst radius is around 0.15. Look at the worst concave points. Look at the worst area, mean concave points, mean concavity, things like that. So most of them are not zeros like decision tree. Most of them are higher than 0. So that's to tell you that random forest is actually better than decision tree because it's a collection of trees. We could also adjust the number of trees that we have there. But it's just that the higher the number of trees, the more the model becomes complex, and that may overfit more. You can change it to 150. You can see it's even better, it's even reduces. So maybe we'll put 200 or 300. So you can run for loop to check as many. You can see it's reducing, and the test accuracy is not affected. So normally the random forest perform better as you increase the number of trees. So as I increase it now, it's not increasing anymore. It's not increasing anymore. So 200 may be fine, and then we can play around all of these ones. So the max depth is mainly the one driving the feature the overfitting or not. Okay, so Those are things you can play around. One final one I will look at is the boosting. And it also uses decision tree, but it works is slightly different from the from bagging, the random forest. Remember, random forest have make sure each tree is independent and they randomly select the variables with replacements to build the tree. But the way boosting works, whether gradient boosting or SG boost, like we'll look at, is that it also has collection of trees, but each tree is trying to correct the mistakes of the previous tree. Like the first tree will be built, is like it's using weak trees called weak learners, like trees that are not so powerful, shallow trees whose depth is very low, maybe depth of 1 or 2. And then we know the tree will not perform well, but the second tree will look at the mistakes of the first tree and will try to correct it while building the tree. The third tree will look at the mistake of the second tree and will try to correct it while building the tree. The fourth, and so on like that. So that's the idea of boosting. The trees are built in a serial manner, meaning after the first tree, the second tree is built, then base is built, trying to correct the mistake of the first tree, the third tree is built, trying to correct the second tree, and so on and so forth. Does it make sense to you?
Yes, sir.
Don't worry. As you go over this over and over, most times in the past, this has been at the PhD level, but now it has been brought down at least. So if you go over the record over and over and then you try this, you will see that you have a very good understanding of it. And yeah. So from scikit-learn is still an ensemble method because the collection of trees. Let's import gradient boosting classifier. For regression problem, use the gradient boosting regressor. Okay, so let's instantiate it using GB gradient boosting classifier. So we use the default hyperparameter. Let's fit it to the X train and Y train. And then we can check the accuracy on both the training and the testing. So this also overfit, but notice that the result is a little bit higher than that of random forest. So let's check. Yeah, this one doesn't even have, it doesn't have random states. Do you observe? Because it's not randomly selecting variables, no. But for those, okay, it has, sorry, it has. So I always like to set it because so that for reproducibility result, for, oh, sorry, I didn't put equals to. For reproducibility, okay, 95.8. So let's check the maximum depth. See, N estimator is also 100. So maximum depth by default is 3. So maybe I should change it to 2, and you can also tune the learning rate. Learning rate is how strongly each tree is trying to correct the previous tree. If it is too high, that means the tree will be trying to correct, will be harsh on the mistakes of the previous tree. You don't want it to be too small, you don't want it to be too high. So you can also adjust that. We can adjust the number of trees, we can adjust the maximum depth. Let me put the maximum depth, max depth, to be 2. Let's see the effect. Oh, it doesn't, it's still overfitting. Look at this now. When I set it to 1, just one level, the training reduces to 99.5 and the testing goes up to 96.5. Actually, boosting has been shown to perform well, to win a lot of machine learning competition. So if you have your main model that you should focus on, you can try all of that one like KNN logistic regression, but the one you should make sure you end up with most times random forest and boosting, be it graded boosting or SG boost like we'll see. So you can see this is very, very, and we have not even adjusted the learning rate. So we can also, okay, that's what I put here, I even try it here, and so we can even adjust the learning rate. We can adjust just the learning rate alone. And we can even combine the learning rate with the max depth of 1. So like that, you can try, but it reduces. So maybe I can move this, and we can even move the learning rate maybe 0.02 or this over fit. Or maybe I can now combine that. So a lot of stuff, a lot of, you can see this reduce this, but the test accuracy also reduce. So you can play around the hyperparameters, play around it, and especially when we look at hyperparameter tuning. So you will be playing around all of these, and will show you a better way of pruning and all of that, of tuning your model to get very, very good results. So that's mainly about boosting. Mainly boosting and random forest, they are very, very powerful. Sometimes boosting is performed better than the random forest. Sometimes they perform equally. Do you have any question before I look at the SG boost and we end the class there? Any question?
No, sir, not really. I understand this gradient system. I think it's actually it's better than the other ones. The way I'm saying.
Okay. So the final one, SG boost. SG boost is not actually different from gradient boosting. It's just SG boost was created for large scale problem. It's very fast because if your data is very large, sometimes random forest and gradient boosting may be slow, but SG boost is fast. SG boost is fast. So it's doing the same thing as gradient boosting, but it's fast. So you have to install the package. You have to run pip install SG boost in a different node, a different cell before you have to install the package because it's not in scikit-learn. So you have to install it. That's why I put this pip install SG boost. So you can uncomment it, put it in a different cell. Okay, so when you are done, you can now import the SG boost. And then from SG boost, you can import the SGB classifier. So we are doing almost the same thing like we did for gradient boosting. We are still using number of trees to be 100. We are still using a very shallow tree of depth 1. And jobs is not doing anything. It's just to make the mode use all of the CPU cores on your computer to train, just to make it faster. Then we can train it on the X train and Y train, and we check the accuracy on both the training and the testing. So if we do that, you can see it takes some time, and then we'll get these results. Okay, so and if you check the documentation, look at the parameters, you can also check the learning rate, just the same thing as the gradient boosting. You can adjust the gamma, you can adjust different hyperparameters. Yeah, reg alpha, that's the L1 regularization time. The reg lambda, that's the L2 regularization, like we did for ridge and lasso. So you can adjust a lot of hyperparameters. Most of these boosting and bagging, like random forest, they function well when you are able to tune the hyperparameter. So that's where the bulk of the work is. You should be able to spend quality time tuning the hyperparameters. That way you will get a very, very good result. So I want you to continue on the Titanic data, but try out, yesterday I told you to try out the KNN and the SVN. Today, try out, on that same data, try out random forest, gradient boosting and SG boost, and compare the result to KNN and SVN. And also do some hyperparameter tuning. Tune the parameters to see which one. Okay? So I don't know if you have any question before we end the class.
Yes, first, my XG boost, when I tried to install it, it was telling me you may need to restart the kernel to use your VTech package or something.
Yes, it doesn't mean. So when you now run the model, does it work? So what it's trying to tell
No,
you,
it's
you
saying
need
that
to
the
restart it.
XG boost,
So you might need to just click on kernel and click restart. But sometimes if you do that, you will have to, then you can now comment it out. Comment it out when you restart. But sometimes you may now need to load in the data again and all of that because it will restart all the cells. So you may need to now rerun most of what you have run before, like the data and all of that. But once you have installed it once, comment it out so that you don't install it again and then tell you to restart and all of that. So just restart your kernel and rerun your model. Restart it and then click on restart and run, or click on restart and run. But before you click on it, make sure you comment where you install the SG Boost. Does it make sense?
yes, sir, yes, sir.